This is Physics 1, Lab 3. The purpose of this lab is to find the mass of the black hole and the initial velocity the spaceship must have to get close enough to the black hole without crashing and leaving the system. Our results that we found is that the mass of the black hole is 1.2 times 10 to the 34, and the initial velocity of the spaceship is -6 times 10 to the 6 in the x direction and 1 times 10 to the 7th in the y direction. This lab uses Newton's second law, also known as the momentum principle, as well as Newton's law of gravitation. We know from Newton's second law that F net is equal to dp dt, and F net is equal to the perpendicular and parallel components of F net added together. We know that F net perpendicular changes the direction, and F net parallel changes the magnitude. Using the momentum principle, we can find our velocity and position update formulas shown here. The universal gravitation law is known as -g m1 m2 over r squared times r hat. The universal gravitation is not constant, so V average is replaced by Vf in our velocity update formula. Because we are in space, we assume that the only force on the system is the gravitational force due to the planet. So we can say that F net is equal to Fg. And F net is equal to dp dt, so Fg is equal to dp dt, so g m1 m2 over r squared is equal to dp dt. From here, we can solve for m1, which is the mass of our black hole in this case. Here are the initial conditions for our GlowScript code. We know g is a gravitational constant, and then we set the mass of the star and delta t as 24 times 60 times 60, because we're trying to make 1 day in seconds. The system we define as the black hole, and we say the surroundings is the star. We see that F net equals dp dt, so we can find the F net parallel component and the F net perpendicular component, which we can add together to find F net. Here we calculate the mass of the black hole using the F net that we found in the previous slide and the formula that we defined earlier on in the presentation. At the end, we print the F net parallel, F net perpendicular, and we print the mass of the black hole earlier on. We find that the mass of the black hole is 1.20853 times 10 to the 34th. F net is 8.28749 times 10 to the 14th. The parallel component of F net is 3.5438 times 10 to the 13th, and the perpendicular component of F net is 8.28191 times 10 to the 14th. So what does this mean? What is the difference between F net and dp dt? Although the values are similar, the method for calculating dp dt and F net is a little bit different. dp dt is a little bit easier to calculate because you only need the planet's velocity and mass, whereas when you're finding the F net, you need more, such as the planet mass of the black hole, in order to solve for the gravitational force and therefore F net. Part 2 of the lab asks us to find an x and y velocity of a spaceship that will allow it to move past a planet and a black hole without crashing into either one. We set the mass of the black hole as what we found in part 1 of the experiment, which is 1.20853 times 10 to the 34. The other initial conditions are given to us. After playing around with the code, I found that a speed in the x direction of -6 times 10 to the 6th and a speed in the y direction as 1 times 10 to the 7th worked so that the spaceship could move through without crashing. We find the initial velocity and the closest distance as shown. The what if part of the lab asks us what initial velocity our spaceship would need to have in order to enter into an orbit around the black hole without crashing into the black hole or the planet. I was not able to figure this out, but in order for the planet to enter into an orbit without crashing, the velocity would have to be large enough to counteract the gravitational force from the black hole and the planet. One possible source of error could be that our time interval was too small in order to accurately predict what we were trying to find, or rounding throughout the calculations could have messed up our numbers.